Welcome to the Steady Thermal Aero Research Turbine Lab, also known as the START Lab, which includes two main areas. On one side, we have several test rigs for studying heat transfer of additively manufactured components that are used in gas turbines. On the other side, we have a turbine test rig that simulates a jet engine and uses real engine hardware. In this video, we'll focus more about the additive side of the START Lab. Turbine vanes and blades have internal cooling passages to keep the parts at safe temperatures. Here at START, we've made a rig to study the heat transfer and pressure loss of unique internal cooling channels that are produced via additive manufacturing. The design freedom offered through additive manufacturing allows for the creation of multiple unique and complex internal cooling geometries and film cooling holes that would be challenging and costly to produce using traditional fabrication methods. For internal channels, we have found that build direction has a significant influence on Nusselt number augmentation and friction factor augmentation compared to smooth channels.
Turbine parts also have cooling holes on the outside to create a protective film and keep the parts cool. We made this rig to study the effects of film cooling with additive manufacturing. We have coupons with different shapes of cooling holes, and we use an infrared camera to evaluate the cooling effectiveness of each design. Additive manufacturing allows us to quickly build and test a lot of interesting turbine coolant designs.
New materials are being integrated into turbine engines, not only additive parts, but ceramic parts as well. Ceramic matrix composites, or CMCs, have a woven surface which is very different from cast parts, and I'm working to understand the effects this woven shape has on heat transfer. We used textile generation software to create a 3D weave model, integrated that surface into a 3D coupon model, and used additive manufacturing to print the part. Since the additive process adds roughness, we printed parts at several scales to ensure that the roughness due to the printing process isn't affecting the results.
Dirt injection is a major concern for aircraft engines. If dirt accumulates on hot components in the turbine, it can lead to higher temperatures and failure of critical components. With this rig, we are studying how dirt accumulates in combustor liners and how these parts can be designed to minimize dirt accumulation. We can run two different kinds of tests. The first test utilizes a slug feed mechanism. A clump of dirt is placed in the section, the valve is opened, and dirt is injected into the test section all at once. For the other kind of test, we can use a continuous feed, which allows dirt to be more gradually added. Dirt is placed on a flat plate upstream of the test section. This capillary tube moves along the length of the plate, causing the dirt to be blown continuously into the test section.
This is the high-speed linear cascade rig, which allows us to study heat transfer and aerodynamics on stationary airfoils at engine-relevant Reynolds and Mach numbers. The same compressors used for the turbine rig deliver air to the cascade test section. The cascade's modular design allows for quick changes to test hardware and instrumentation. The airfoils themselves are 3D printed and include pressure taps so we can measure aerodynamic loading. We also use an infrared camera to measure surface cooling effectiveness, a linear traverse for probe measurements, and a particle image velocimetry system for detailed flow field measurements.